you. How are you?
Yes, I'm fine. I'm Darmawan Stianto from Department of Dental Public Health, the staff of Dr. Taufan.
Oh,
I
it's
will
nice to meet you.
listen. Thank you very much.
Finally, we meet here in Zoom meeting after
Yeah.
we have a discussion from Cornelia, and I think
Yes.
Cornelia has already came to here also, join with us in Zoom meeting also.
Yeah, she is here too.
Oh, I see. Okay, Cornelia. Yes, of course.
She will support me and
Okay.
strength.
Okay, thank you very much. Become our guest lecturer, and hopefully we can learn much from you regarding especially about regression analysis, because regression analysis is become one of the important analysis in statistics, I think. So we must learn from the expert, and hopefully we can have a lot of information from you. Thank you.
Thank you. It is an honor to have here and can present some slides.
Yes. And Kia, silakan dimulai Kia.
Ya dokter.
Ya silakan dimulai Kia.
Ya untuk ini nanti jangan lupa untuk mahasiswa terutama yang semester 5 untuk absensi sesuai dengan ketentuan. Setelah ini nanti akan langsung dipimpin oleh Dr. Dini, ya dokter. Mohon izin.
Oke. Start now?
Ya dokter, silakan dok. Boleh dimulai sekarang.
Okay. Good afternoon, everyone. Welcome and thank you for joining in our Stovit online series hosted by Faculty of Dental Medicine, Universitas Airlangga, Surabaya. My name is Dini Setiawati and I am the moderator for our today's webinar. We will have a lecture that will be delivered by Dr. Attila Nagy from Faculty of Public Health, University of Debrecen. Is it correct spelling, Dr. Nagy? How to spell it?
Yes, yes,
Okay.
It's good. Thank you.
Yes, Hungary. At the end of each session, we allocate 15 minutes for discussion, so all participants are welcome to send a question to the speaker through our Zoom chat room. Before we start the lecture, I'd like to welcome our remarkable speaker, Dr. Attila Nagy. Good afternoon, Dr. Nagy.
Good afternoon.
Thank you for your time and your willingness to give a lecture in our today's webinar. It's been an honor for us. Before Dr. Nagy starts giving the lecture, let me briefly read his curriculum vitae to introduce him to all of the participants. Ladies and gentlemen, our speaker for today's webinar is Dr. Attila Nagy. He is an assistant professor from Faculty of Public Health, University of Debrecen, Hungary. He has a lot of educational background and courses. He earned his medical doctor in Hungary in 2005. Then he completed his master's degree in 2011 and got her PhD in 2015. He also has a great number of published academic articles. Okay, as now it's already at 3 p.m. Indonesian time. Let's start the lecture. I'd like to invite Dr. Nagy to start his lecture about effective strategy on regression analysis. Dr. Nagy, you have around 45 to 50 minutes to give your lecture and 10 to 15 minutes for discussion. You may start your lecture now. Thank you, Dr. Nagy.
Okay, thank you very much. Good afternoon, everyone. I will share the slideshow. Okay, so good afternoon. I would like to speak or have a short presentation on regression analysis. I would like to refresh your knowledge related to statistics, some basic statistical slides, and then about regression. Here you can see the main steps in the statistical work. First, usually we start with the data management. The data management consists of three main steps: data collection, data entry, and data checking. Usually we have to check whether data are entered correctly, whether they have a meaningless range, no invalid values. Sometimes we do a double data entry. It takes more money and time, but it's worth it because then we can compare the two databases, we can check for differences, and we can correct them. Then, after the proper data entry, we have to fill the data set. We must have a picture of the data set. We should have descriptive statistics. For continuous variable, we usually use mean and standard deviation. For categorical variables, we check the proportions of the different possible answers. And then, after having a picture of the database, we can go further and we can perform more advanced data analysis, some univariate analysis and multivariate analysis like regression as well. Then we have to check the results, and finally we interpret our results and our findings. As you know, here we can see what is null hypothesis and what is the research hypothesis. Usually based on observations, we will have a research hypothesis. Research hypothesis always said there is an effect, there is a difference, there is an association, there is a relationship between two factors, between a possible exposure and an outcome. Null hypothesis is always the opposite. It says there is no effect of, for example, a given drug, no difference between, for example, means of different groups, no association between an exposure like smoking and a given outcome like, for example, brain cancer, and no relationship between an exposure and an outcome. Here you can see a summary slide, how things work and how scientific methods are working. So based on the observation, we will set up a research question which will lead to our hypothesis. The research hypothesis will say there is an association or there is a difference between group averages, and then we will have some predictions after the experiment and the results. Hopefully it will lead to a theory which we can discuss. Otherwise, we have to reject our hypothesis in case of non-significant result, non-significant associations, and then we have to refine our hypothesis and go further again and again until we have a significant result and we find a true association. The confidence interval and the p-value, they move together. The sum of the p-value and the confidence interval is 1. We usually use most commonly the 0.05 p-value. P stands for probability. Probability of having the result because of some error, because of unlucky sampling. And if the probability of having the result because of some error is less than 5%, 0.05, then it's more than 95%. So it's pretty sure that we have a true finding, a true significant result. So that is why for checking significance, we usually use this p-value. And why are we using the 0.05? Because this 0.05 or 5% is the evidence-based p-value. If we use this, the false positive and false negative results are pretty well balanced. So that is why we are using this 5% p-value. As I said, the p-value and the confidence interval are 1 together. So if we use this most commonly used 0.05 p-value, then the fitting confidence interval is 95% confidence interval. To get this 95% confidence interval, if we check the standard normal distribution, here you can see this Gaussian curve. this bell-shaped curve, which is the normal distribution. Many parameters follow this distribution, like BMI, weight, height. So most of the observations are around the mean. And as we go towards less and less frequent values, then we will have less and less observations. We call the normal distribution standard normal distribution when the expected value is 0 and the standard deviation is 1. The other name of this standard normal distribution is Z distribution. Here you can see this Z or standard normal distribution. So the mean or the expected value is 0 and the standard deviation is 1. If we think this is a probability curve or we check it as a probability curve, then under the curve the total area is 1 or 100%. If we would like to cover 95% of it to fit or to fulfill this 95% confidence interval, we have to cut at minus 1.96 and plus 1.96. Because if we cut there, we will cut 2.5% from below and 2.5% from up. The total 100 minus this twice 2.5 will get us the p-value 0.05, and the remaining area, this 95%, should go to the confidence interval. So to get this confidence interval and to have the remaining 95%, we should cut at plus and minus 1.96. And if we have, for example, BMI values, then we have to shift this curve to our situation. So instead of the 0 mean, we will use our sample mean, like for example 22. And instead of the ideal big sample size n, and instead of the standard 1 standard deviation, we use our standard deviation and our sample size. So if it's a continuous variable, like for example BMI, then we can calculate the 95% confidence interval. If we calculate the standard error, like instead of the ideal 1 standard deviation, we use our sample standard deviation, and instead of the ideal big sample size, we use our sample size. So standard error is a measure in which the standard deviation and the sample size are combined. So the standard error is the standard deviation divided by the square root of the sample size in case of a continuous variable. The general formula for the 95% confidence interval is the point estimation plus minus 1.96 times the standard error. The point estimation is one number, the most likely parameter based on our sample, by which we represent the source population. So if it's a mean, then the point estimation is the average or the mean, for example, of a BMI. Plus 1.96 times the standard error for the upper border, minus 1.96 times the standard error for the lower border. The standard error, as I said, for example, BMI and for other continuous variables are the standard deviation divided by the square root of the sample size. But this is the general formula for all confidence intervals. So the point estimation could be a mean, could be a regression coefficient, could be a standardized death rate, for example, or it could be a relative risk for a cohort study, or could be an odds ratio for a case control study. So no matter what is the measure, what we calculate, the point estimation plus minus 1.96 times the standard error will give us the interval estimation from to range, the confidence interval. And the standard error is always, we should adapt it to the point estimation. So for continuous variable, is the standard deviation divided by the square root of the sample size. For relative risk, we have a different standard error. For proportions, different standard error. Odds ratio, different standard error. But always 1.96 times the standard error to add and subtract from the point estimation to get the lower and upper border of the confidence interval. Here you can see the most frequently used parametric tests. Usually, here we can check the distribution, whether it's normal or not. For normality, it's very important to check it, because for different tests, it's an assumption to have the variable as a normally distributed variable. Then we can use parametric tests, which could be seen here. These parametric tests are stronger, so they have larger statistical strengths, but they need some assumptions to fulfill, like normality. Otherwise, we can use non-parametric tests, which are weaker. For example, by t-test, we compare means of different groups. If the continuous variable doesn't fulfill the normality, then we have to use the non-parametric pair, the Wilcoxon test, in which we compare medians, the middle values of the continuous variable, not the means. This normality could be tested, for example, by the Shapiro-Wilk test, which is commonly used, and stronger, more statistical power compared with, for example, the Kolmogorov-Smirnov test. So if the normality is fulfilled, then assuming this normal distribution, we can check which test could be used in case of which statistical problem, in case of which hypothesis. So if we have one group and we would like to compare the average of this group, for example, whether the research question, we have a class and the average BMI in this class differs significantly from 25 or not. Then we have one sample and we compare one average with one constant number. In this case, we use the one sample t-test. The assumption is normal distribution, we have one constant number and we compare it. If we have one group and we have some intervention and we would like to check whether it has an effect and significantly changes, for example, the systolic blood pressure after taking a drug, then we have to use the before mean and after mean, and we would like to compare them. Then we use this paired t-test. We have before and after, or pre and post values, then the paired t-test, what we need. The two sample t-test, we have two different samples, two different classes, for example, and we would like to compare their averages. Then before this t-test, mainly in Excel, we should perform the so-called f-test, which is for comparing the variance or the standard deviation, because variance is standard deviation of the second. So the standard deviation or the variance of the two groups, if they have the same variances, then they are homoscedastic equivariance models. Otherwise, they are heteroscedastic different variance models. If we have two groups and two means to compare, then t-test after f-test. We can even calculate the average and calculate the 95% confidence intervals. Here you can see the way of calculating it. So the average plus 1.96 times standard deviation divided by the square root of the sample size for one group, for two groups, even for more groups. And then we can check for the confidence intervals. If they overlap, then they are the same, no significant difference between them. If there is no overlapping, then it means the difference is significant. And if you would calculate the p-value, it would be less than 0.05. So the confidence intervals and the p-values are moving together. To compare more than two groups, one way to solve this task is to calculate the average and the confidence interval. The other way is to use this ANOVA, which is the one-way analysis of variances. It calculates and deals with variances, but it's a bit misleading because it is for comparing means, not variances. So it uses variances for the background calculations, but it compares means. So the null hypothesis, all means are the same. The difference between them is zero. Research hypothesis, there is a significant difference between the means. We can even perform chi-square test for categorical variables. If we have categories and observations, like for example, we have the gender and male, female, and we have, for example, diabetes, diabetic patients and non-diabetic patients, and we would like to check whether there is an association between the two categorical variables, gender and having diabetes, then we can perform a chi-square test. In this chi-square test, we check whether they have the ideal distribution or some kind they are associated somehow. And the H0 of the chi-square test, there is no association between the categorical variables. They have the same distribution, no matter whether female or male, or they are together, the same proportion of them will have diabetes. In case of a significant association, when we reject H0, when the p-value is less than 0.05, it will show us an association, and it will show us there is a significant association, for example, more prevalent diabetes among male than female, then it means there is a significant association between gender and having diabetes. For continuous variables, we can check the effect of the continuous variables. For example, blood sugar and BMI, whether they have an association or not. Whether it's positive association, they are risk factor of the outcome and it increases, they increasing each other, or whether it's a negative or inverse association, protective factor, like vaccination will protect us from diseases, or neutral, no association, that is the H0 value, and linear regression could show this, whether they have an association or not. Even correlation can show this between two variables. I will tell you some words on correlation as well, and what is the difference between correlation coefficient and regression coefficient. But the main difference for linear regression, we can have more than one variable. So whether we would like to know blood sugar depends on what. If we would like to compare the association or check the association between blood sugar and BMI, then it's a univariate linear regression because one explanatory variable is used for the outcome. If we use more than one, like we would like to check the effect of not only the BMI, but also the age on blood sugar, then it's a multivariate linear regression. More explanatory variables are included in the model. Based on the regression models, or related to the regression models, based on the outcome, we can distinguish between them. The outcome, what we are investigating, for which the exposure or the association should be identified. So if the outcome, for example, is the diabetes, whether someone has diabetes or not, it's a dichotomous, it's a binary variable, yes or no. If we would like to check the association between a continuous variable like concrete blood sugar values, which can have nearly infinity values, then it's a continuous outcome. Then here are the two main groups, continuous and dichotomous or binary. If it's continuous, depending on the predictor variable, if it's categorical, we can use something called ANCOVA, analysis of covariances. Not, then we use the linear regression in case of one explanatory variable, univariate linear regression in case of more than two equals or more than two, so more than one explanatory variables, we use multiple linear regression. If we have a binary outcome, depending on the time to event availability, if it's, for example, a survival analysis, when the outcome is binary, survived or not, then having time to event availability, we can have a so-called Cox regression, Cox proportional hazard regression. Otherwise, we can use a logistic regression when the outcome is binary, yes or no, 0 or 1. In case of one explanatory variables, univariate. In case of more than one explanatory variables, multivariate logistic regression. For linear regression, here you can see some case statements related to the association between the two continuous variables. I underlined the most important research question: is there a linear relationship between two variables? We have two continuous variables, and whether they have a significant association relationship or not. Here you can see one example. How does serum cholesterol level related to waist circumference? We have two variables. If we have on an axis, x and y axis, then we have two. Usually we use exposure on x and outcome on y axis. We use scattergrams or scatter plots. We have individuals, not groups, and we plot each individual. So we have this waist circumference 100 with this cholesterol level 4. This waist circumference 150 with this cholesterol level 5, and so on. So we plot each observations, and then at the end we try to fit a line. As I said, usually the exposure is on the x-axis and the outcome is on the y-axis. The equation of the line y equals b times x plus a, or beta and f. The outcome, or the other name is the dependent variable, usually is on the y-axis. The explanatory variable, or the other name is independent variable, usually on the x-axis. If we have one outcome and one explanatory variable, then is the univariate linear regression, because one explanatory variable is used. If we use more than one explanatory variables, then is the multivariate linear regression. A is the constant and B is the coefficient, the regression coefficient. Here you can see the assumptions which should be fulfilled in case of a linear regression. Y should be a continuous variable. So binary variable is not good, 0, 1. Discrete few categorical variables, not good. If you have, for example, education levels, primary, secondary, tertiary, it's not good. We need continuous, which have enough discrete variables, at least 10 or 20 categories, or continuous variables, which can have nearly infinity values, like a BMI, someone could have 18, 22, 22.1, 22.22, and so on, so nearly infinity values, so the y should be continuous. The observations on y are independent. There is a stochastic linear relationship between the two outcome and the explanatory variables, and the distribution should be normally, or at least approximately normally. It means it's not necessarily a problem if it's not normally distributed, but it should be close to it. And the standard deviation of y doesn't depend on x, so homoscedasticity should be there. This approximately normally distribution means if we use, for example, the Shapiro-Wilk test, the H0 of this test, the null hypothesis, there is no significant difference from the normal distribution. If the p-value of this test is less than 0.05, it means there is a significant difference between normal distribution and our distribution. So our distribution is not normally distributed. So to have a normal distribution in this test, I should have p-value above 0.05. If it's below 0.05, it means we reject H0, the null hypothesis, and we accept our research hypothesis. There is a significant difference from normal distribution, and our distribution is not normally distributed. If the p-value is close to 0.05 but less, like 0.04, we should reject the H0 and we should tell it's not normally distributed, but it's very close to 0.05 quasi borderline significant result, so it's close to normal distribution. In this case, we can use linear regression because it's approximately normal distribution. If we have a very strong p-value, like less than 0.001, then it's not normally distributed and not approximately normally distributed. Okay, so scatter plot or scattergram is used for visualizing the regression. If we have one explanatory and one outcome, then here is what it looks like. Then we try to fit a line And for the first site, we can see if this line is increasing, if it has an elevation, then it means it seems a positive association or a risk factor. If it has a decrease, then it would seem an inverse or a negative association or relation. The stronger elevation, the most likely to be significant. If it's a slight elevated line, then it's perhaps not significant or borderline significant. The equation of the line is y equals beta times x plus a. In this case, y equals beta times x plus a. So cholesterol level y equals 4.04 plus 0.011 times x, the base waist circumference. So back to this equation, b or beta in our case is 0.011 and a is 4.04. What does it mean? If x is 0, then 0.011 times 0 is 0. So cholesterol level will be 4.04. This means this line cuts y-axis at 0.04. In case of zero waist circumference, the cholesterol level would be 0.04. This B means 1 unit increase on the x-axis will increase the cholesterol level by this amount. So plus 1 centimeter waist circumference will increase the cholesterol level by 0.011 millimole. So the constant, in this case it's 4.04. It has the same dimension as y as the cholesterol level, so millimole per liter. And it shows us what is the expected value of y when x is 0. So where y-axis is cut by our line. B, the same dimension so dimension of B is the dimension of y divided by dimension of x. So in this case, millimole per liter per centimeter. So this is the dimension when we divide the two axes. And it means 1 unit change in this will increase or decrease y by this amount. So if it's a positive association or relationship, then 1 extra centimeter will increase the cholesterol level by 0.01. Otherwise, if it would be minus 0.01, it would mean there is an inverse association or correlation, and 1 extra centimeter would decrease the cholesterol level by 0.01. H0 value, no association between the exposure and the outcome, or between the exploratory variable and the outcome. And here is the statement of the H0, beta equals 0. So in case of 0 coefficient, no association between the exposure and the outcome, the line would be parallel with the x-axis, and no matter whether 100 centimeter or 200 centimeter, the outcome cholesterol level would be the same, like 4. So if beta is 0, it means it's not a true influencing factor, not a risk or protective factor, no association at all. If we calculate, or the statistical program will calculate us the confidence interval, if we check the confidence interval, so as I said, there is always a point estimation, like a regression coefficient, and an interval estimation from to range. If the lower border of the confidence interval is positive, like 0.01, and the upper border is still positive, like 0.02, then it is this situation, the third one. Positive lower border, positive upper border, and of course, positive point estimation, because the confidence interval is the point estimation plus minus 1.96 times the standard error. So the point estimation will be always inside the confidence interval. We have to look for the H0 value. In this case, by regression, the H0 value is 0. So if 0 is inside, it's a wide unsure estimation. If it's outside of the confidence interval, then it means it's significant. So if the lower border, upper border, and the point estimation, all of them are positive, then we have a significant positive association. 0, the H0 value is not inside the range. If all numbers would be negative, like minus 0.01, lower border minus 0.2, upper border minus 0.1, then it would mean it's a significant inverse association. 0 is not inside the range. If 0 is inside, it's a wide unsure estimation, protective risk, no association. So the interpretation is always the opposite. H0 is inside, not significant. H0 is not inside, significant. If the lower border is less than the H0, less than 0, and the upper border is above the H0, above 0, it's a wide unsure estimation, it's not significant. And what it seems, it depends on the point estimation, the regression coefficient. If, for example, here the lower border is minus 0.1, the upper border is plus 0.1, then it is inside, the H0 value is inside, not significant. And what it seems, if the point estimation, the regression coefficient is plus 0.01, it seems positive, but not significant. If it would be minus 0.01, it would mean it seems inverse, but it's not significant. Here you can see an output of a univariate linear regression. It is from a statistical program called Stata. In this program, we use the regression and we should put first the outcome, then the explanatory variables. This is the output, what it provides. Here we can see the number of observations. 23 people are in this group, and they have both the outcome and the explanatory variable values, no missing values. And what is interesting here is this R-squared value. This R-squared value shows us how good is the fitting of the line on the points. If it's totally fitted, so all 23 observations would be on the line, then it would be 1 or 100%. In this case, it means it is 70%, not so strong, but still 70% the strength of this model, because 70% of the points are on this line. The outcome y equals the constant plus coefficients times the explanatory variables. So back to our previous example, the outcome was the cholesterol, the constant was 4.04, the explanatory variable was the waist circumference, the coefficient of it was 0.011. So in this case, we can check the coefficients, both for the constant and both for the explanatory variable or variables in case of a multivariate linear regression. Standard error is not important for us. It would be important if we should calculate the confidence interval, because 1.96 times the standard error would give us the upper and lower border. But in this case, the statistical program calculates it for us. The t statistical number is not important. From this, the program will calculate us the p-value. And here we have the p-value. If the p-value is less than 0.001, Stata says 0.000. So it's not 0, just a very small p-value. In this case, by the explanatory variable, the p-value is less than 0.5, very close to it. So it's a borderline, but still significant, less than 0.05. So in this case, the point estimation is positive, the regression coefficient, meaning that in case of 1 unit increase in the explanatory variable, will increase the outcome by 0.02 units. The confidence interval starts at plus 0.0002, ends at plus 0.04, meaning that it's significant. The confidence interval has two meanings. One, if we repeat the study 100 times, 95 times, we will get point estimations in this range. 5 times because of unlucky sampling out of this range. The other meaning, the true population parameter, which we never know, unless we measure the total population, but we don't have money and time for that. So we just draw a random representative sample and do the measurements among them. So this other meaning 95 is the probability that the truth, the question population parameter, is in this range. So it's positive, positive, point estimation positive, it's a significant positive association or relationship. If we have more than one explanatory variables, then we should write it after the first one, x2, x3, and so on. And we have not one, but more than one lines. And the equation of the line outcome equals the constant plus or minus coefficients times x1 plus or minus coefficients times x2, and so on. If we would check a correlation, it would very similar to this. So we check the correlation between these two variables, but the one mean difference correlation could be checked only between two variables. If we have two continuous variables, we can check the correlation between them. For linear regression, we can have more than two variables together and more than one explanatory variables. We can even have not continuous variables, categorical, or even binary, like gender. Then we have points for male, points for female, and then line is fitted. By correlation, we can have only two continuous variables. The other difference, the range. For correlation coefficient, between -1 and +1 is the range. +1 is a total 100 moving together in a positive way. -1 is a total inverse moving together. 0, no association, no correlation between the two variables when the line is parallel with the x-axis. By regression coefficient, it can have values between -infinity and +infinity. And it means one unit change in the x-axis will change y-axis with how many units. So this is the unit change, the regression coefficient. 0 is the H0 value. Correlation coefficient, still 0 is the H0 value, the no association value. But it shows how strongly they are correlated, they are moving together perfectly, or 0.5, 50%, or -0.2, -20%. For logistic regression, the outcome is binary, as we discussed. So here we have the logistic regression, dichotomous, categorical, and even inside the categorical binary, yes or no outcome. And odds ratios are reported. The odds ratio H0 value is 1. Here you can see a logistic regression output. Logistic output binary, yes or no, and explanatory variable. Odds ratios are reported. The p-value seems very significant, very strongly significant, and here we can see the confidence interval. By odds ratio, the H0 value is 1. 1 times higher odds, the same odds, no matter whether they were exposed or not. In this case, it's a pretty high. It means 50 times higher odds for exposed to have the outcome compared with unexposed. Confidence interval, 1 inside the H0 value, so it's significant. Worst case scenario, 30 times higher odds or risk. Best case scenario, 80 times higher. Most likely 50 times higher. Like if it's, for example, diabetes and the explanatory variable is obesity, then obese people have, for example, in this case, it's a hypothetical example, but it would mean obese people have 50 times higher odds for having diabetes compared to normal or underweight. So 1 is the H0 value of the odds ratio. Lower border less than the H0, less than 1. Upper border above 1, not significant. All numbers, point estimation, lower upper border less than 1, it's a significant protective factor. All numbers above 1, it's a significant risk factor. In this case, above 1 point estimation, above 1 lower border, above 1 upper border, it's a significant risk factor. If the lower border would be less than 1, like 0.2, then it's not significant, but it seems risk. If the point estimation would be less than 1, 0.4, lower border less than 1, 0.3, upper border above 1, then it seems protective, half risk for exposed, but not significant. If all numbers below 1, 0.4, 0.3, 0.7, then it's a significant protective factor. They have less risk compared to unexposed to get the outcome, like vaccination, for example. And our last regression is the Cox regression, proportional hazard models. It is used for survival analysis, and it reports hazard ratios. The interpretation of hazard ratio is very similar to odds ratio. 1 is the H0 value, above 1 risk for the outcome for dying, and below 1 protective. Kaplan-Meier curves are used for visualization. Here on the y-axis, we have the total survival, 100%, and the exposure is the time. At the beginning, everyone survival, 100%. We have two different groups. After a while, it decreases, they die. In the second group as well. And the question, do we have a significant difference between the two groups? For example, drug treatment in group 1 and in group 2, and which is the placebo or which is the more effective, for example, antihypertensive drug. The wider difference between the two lines, the more likely to be significant. Log-rank test could provide us a p-value, but Cox regression could be as a linear regression or a logistic regression, could be uni or multivariate. Different factors adjusted for each other could be investigated whether they are protective or risk factors. Hazard ratio 1 is the H0 value. All numbers above 1, hazard ratio, lower confidence interval border, upper confidence interval border, significant risk factor for dying. All numbers, point estimation, lower upper border, significant protective. Lower border less than 1, upper border above 1, it is not significant. And what it seems, based on the hazard ratio, if it's above 1, like 2, then twice risk for dying. If it's below 1, protective, like 0.5, 50% less, half risk for dying. Here you can see the output of a logistic regression, but it's nearly the same as the Cox regression, but it is not odds ratio, but hazard ratio. There are even more advanced regression methods. Usually in R, it's very easy to have them. Robust regression, it's an ordinary least squares regression is the official name of the linear regression. If the outcome is not approximately normally distributed and not normally distributed, then we can use this robust regression. If we have more than one binary outcome, so not 0, 1, but 1, 2, 3, then we can use multinomial or ordinal logistic regression. If we have count variable, count numbers of, for example, vaccinated ones, then we can use the Poisson regression, and so on. So there are so-called lasso regression for machine learning and so on. And there are different regression methods for different research questions. Related to statistical softwares or software packages or software, R, it's pretty widely used, and it's a freeware software, not so user-friendly, but everything could be solved in R. Python, it's rather a programming language, but still usually in machine learning, deep learning, it's used, and even more powerful could be compared with R, but some programming skills are needed for it. SPSS, widely used, user-friendly, but it's not free. And Stata, perhaps it is the more expensive above all, but it's very powerful, and it's a very fast statistical program. Thank you for your attention. Here you can see my email address if you have further questions or some other statistical questions. Thank you for your attention.
Thank you for your delightful lecture, Dr. Nagy. Maybe, is there any question from the participants, from students, or our statistician, research method lecturers? I will check our chat box first.
Okay, I will check the chat. Yeah.
Okay.
Okay, can I ask?
Okay, sure.
Attila. Okay. If I have two regression models, like y is equal to 15, constanta is 15 plus 1.5x.
Yeah.
And then the other one is y is equal to 0.9 constanta plus 1.5x. What is the difference of this constanta? What is the meaning in the models? The meaning of the models. What is the difference? Because maybe some coefficient of x is the same, but constanta is different. So what is the meaning? What is the difference? Thank you.
Very good question. Yes, so the coefficient is very important for us, and it would tell us the way of the association, whether it's positive or not. And if they have the same, like for example 0.35, yeah, then it means it seems the same positive association, so it's a positively influencing factor. But we still need to know the p-value of this 0.35 coefficient or the confidence interval, because only in that case can we tell whether they are significant or not. It's possible then in the first model it's significant, and in the second model it's not significant. So we have to know the p-value or the confidence interval, and whether the constant is difference, it means that the outcome is not the same or the explanatory variable is not the same. So perhaps they have different dimensions, like one is base circumference, the other is BMI, and the constant shows us where the line would cut the y-axis. So for example, if it's BMI and 15, then it would cut at 15, and the association seems positive as 0.35, but whether it's significant or not, we have to know the p-value or the confidence interval. If the other is 0.1 or 0.2, it would mean the line would cut at 0.1 or 2, or if the base circumference would be 0, which is not possible, but if so, then it would mean the outcome would be 0.1. And in this case, we have to check the dimension, and we have to check the outcome variable, and we should interpret it related to that.
Okay, thank you very much.
Thank you.
Thank you. We also have a question from Dr. Zamzam, and Dr. Zamzam would like to ask you directly. I will invite Dr. Zamzam to unmute yourself and ask to Dr. Nagy.
Okay, thank you, Dr. Dini. Nice to meet you, Prof. Nagy.
Nice to meet you.
Thank you for the wonderful presentation. My name is Zamzam. I'm the junior researcher of Dental Public Health Department. So I have some question for you. In our research, in oral health research, especially in community-based research, the data have high amounts of variation with different data scales. As an example, there is a research aiming to address the effect of socio-demographic as determinants as independent variables, such as education level, which is a categorical variable, or the NULL scale, and amount of income, which is continuous variable, numerical scale, to oral hygiene index as dependent variable, which is numerical variable. So we have two independent variable and one dependent variable. My question is, what kind of the best modeling analysis for those kind of variables? Is it multivariate linear regression or some kind else? And how we interpret statistical results when the variable data type or scale are very dispersed in variation, but we want to do the multivariate analysis. Thank you, Prof. Nagy.
Thank you for the question. Yes, it's a good question. So if we check, for example, the linear regression, the univariate linear regression, and the correlation, then, as I said, the regression coefficient and the correlation coefficients are different. The p-value, however, would be exactly the same. So if we have a positive correlation, which is 0.8 and 80% moving together or correlated, then the p-value would be, for example, 0.01. If we check the regression coefficient will be different, like 0.01, but the p-value will be exactly the same, 0.01. Other meaning, but the same p-value. Back to your question, if you have an outcome and you would like to create a model, then I would say it's the best to use, as you asked, a multivariate model. Which variables to include in the model? One possible way is to have a univariate analysis like a t-test or chi-square test, and the significant ones should be included in your final model. The other possible option is to check literature and which were in other literature included, then you should include them too, or you can include them too. And you can even have some general variables which are included. So usually confounders should be included. And one main aim of the regression is to adjust for confounders, because other possible way to adjust for confounders is the stratification. But if we have too many variables and too many categories, then we will lose observations, and we won't have observation at the very last cells, and it would take much time to have it, and that's why we use regression. So the main aim of regression is to adjust for confounders. General confounder is age, gender. So I would include in the model age as a continuous variable, gender as binary, education, level of education, as you said, categorical variable, and in the models you can set different base of the comparison, like primary could be the base, and you compare secondary to primary, tertiary to primary, secondary could be the base, then primary to secondary, tertiary to secondary. So I would include general demographic factors, age, gender, level of education, some social demographic, and perhaps I would check in univariate analysis based on t-test, group, mean, differences are significant or not, or chi-square test, categorical variance, categorical variable associations, and I would include them. And even there are so-called stepwise models in which you can have backward or forward if you, for example, include all variables, and the statistical program will drop which are not significant, and you will have the final model. So you can use different approaches, but hopefully it will lead to the same final model, a multivariate model, as you said, in which hopefully significant variables are.
Thank you, Prof. Nagy.
Thank you.
Thank you. And also there's one more question from Dr. Nino, and I will invite Dr. Nino to unmute herself and ask Dr. Nadi the question directly.
Okay, thank you for the time. Thank you for the wonderful presentation, Dr. Nagy. I just want to ask your opinion about there are so many researchers right now moving from the p-value to the not exact point estimate, like they use confidence interval. I think you already explained to us how to change that one. Are you the kind of the researchers that morally choose the confidence interval opposite to the p-value. Because right now in the journal, we can currently see that many journal rejects the use of p-value and range for the range confidence interval instead. Thank you.
Thank you for the question. Yes, it's a very good question. As I said, the p-value and the confidence interval, they move together. So if, for example, the p-value is significant, less than 0.05, then the H0 value will be not in the confidence interval. If it's above 0.05, then the H0 value will be inside the confidence interval, and it's exactly 0.05, this borderline significant, then the H0 value will be exactly the lower border in case of a risk, or the upper border in case of a protected factor. Using the p-value and the confidence interval could be a bit redundant as well, because they all have the same meaning, but I agree with you, confidence interval is a bit more informative compared with p-value, because p-value can tell us whether it's significant or not, and the confidence interval can tell us exactly. So if we can see without the point estimation, just the p-value, we don't know whether it's risk or protective. If we know the confidence interval alone, without the point estimation, we can exactly tell whether it's a significant risk or significant protective, and we can even tell the range. And it is even more informative based on the research question and the conclusion related to the source population. So I agree with you, and I prefer confidence interval compared with p-value.
Okay, thank you so much. Because what I want to mention here is sometimes our students usually use only the p-value, while right now there is a change or a movement in our scientific research that move not only to the p-value but change to the confidence interval. So it's really good. Your explanation could use by our student to explain more about what their research, so they can probably gain more outcome in the good expected journal for the publication. Could I have a second question, Dr. Nadi? You also mentioned that before we conducted the regression, we should have many things that we need to check. The more important, like the multicollinearity, and then I just need to give the emphasize for our student that all of the one that have explained by Dr. Nadi before, we should check that one. So if you move from the standard regression to the multi-linear regression or logistic regression, multivariate, we should come back to the checking the prerequisite condition. Thank you. Is that right, Dr. Nadi?
Yeah, you're absolutely right. Yes, in the multivariate models, yeah.
Okay, is that enough, Dr. Nino, or is there anything?
Yeah, thank you, Dr. Nino.
Okay,
Thank you.
Okay, I think that's the last question, and we also run out of time now. To briefly sum up this lecture today, we should know which, to analyze our research data, we should know which test that is appropriate, and whether it is parametric or non-parametric test. It depends on the result of our normality test, in which Shapiro-Wilk test is more powerful than Komolov-Smirnov. And for regression models, we should know whether the types of our predictors and outcome variables, and also there are several assumptions that we must pass or we must follow. So this is the end of our lecture with Dr. Nadi in today's webinar. We would like to express appreciation and thank you for your inspiring lecture, Dr. Nadi. It's very interesting to hear about your lecture. Hope in the future we could have a collaboration and re-invite you in our other academic events. Thank you, Dr. Nadi.
I hope that too. It was a great honor. Thank you very much. Thank you.
Finally, thank you for all participants who attend in today's webinar. Hope you can benefit from the lecture and see you in our next Stovit online series webinar. Assalamualaikum warahmatullahi wabarakatuh. Good evening, everyone.
Thank you very much. Have a
Thank
nice
you,
day.
Taki.
Yeah.
Terima kasih, Prof. Terima kasih, Dr. Dini.
Terima kasih, Dr. Taufan.
Thank you everyone.
Thank you so much.
Matur nuwun. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.